speaker. Yes. Very good. Song Han from associate professor at MIT. His research group, the HAM group, specializes in efficiency in neural models. And his group made important contributions in the field of model pruning, quantization, compression, among many others. His work has been cited over 50,000 times. And today's talk is about a slightly different part, namely the edge deployment of a vision language model called VILA.
Okay, hello everyone. I'm glad to talk about our research, VILA, and efficient visual language models. So today's AI are too big. So I've been working on efficient AI computing for the past decade, particularly since 2016. The work on deep compression started using pruning and quantization for modern neural networks to reduce the number of weights and reduce the precision per weight, followed by the efficient inference engine, which can directly accelerate a sparse and compressed neural network with the algorithm and hardware co-design. And recently, pruning and sparsity are getting quite popular with respect to the number of publications. So that's some background. Later, I worked on neural architecture search, basically the once-for-all network, where you can train one network, and surprisingly, you can get 10 to the 19th different subnetworks that can independently operate. So then we can search the best subnetwork based on the hardware resource to enable such hardware-aware neural architecture search. So different from pruning and quantization, which compress an existing model, this technique actually can design an efficient and compact model to start with, and reduce and amortize the search cost by training this once-for-all model, and then have these different specialized models depending on the model constraints, the hardware constraints. For example, if you have a lot of resource, like in the cloud AI, we can run a larger subnetwork. On the right-hand side, if you only have a microcontroller, we can run a tiny model. And this is achieved by a once-for-all model, which is the winner for 3 low-power computer vision challenges, and also is the core technique of OmniML, a startup acquired by NVIDIA. Now NVIDIA also enabled that for once-for-all networks for large language models. So later, I worked on the project called MCUNet to go one step further, bring AI to IoT devices. They are much smaller and much tinier. We co-designed the tiny NAS with the tiny inference engine for algorithm and system co-design, which is very crucial, especially when the design space is very large and also the constraint is pretty heavy. So we can reduce the memory footprint by almost 2x every year until just a few tens of kilobytes to do this person recognition, detection, different tasks. Very lightweighted, just a few hundred kilobytes. So this is about MCUNet for inference, and we believe on the edge is very crucial to also perform training. So we performed on-device training under only 256 kilobytes of memory on this microcontroller. This is enabled by 3 techniques. So one is sparse update. So not all the layers are crucial. We can sparsely update the layers, and we can use quantization-aware scaling to enable 8-bit forward and backward locally on the microcontroller. So quantization-aware scaling related to just 2 lines of code, but can make the training very stabilized. And finally, we worked on tiny training engine to implement the algorithm saving into measured speedup. So initially, the model cannot detect a person versus no person. Now we have 2 buttons. We can press the green button to show there is no person, and press the red button to show there is a person to teach the microcontroller, and everything running locally on the SRAM and Flash. Flash is read-only, only the SRAM is writable, and after a while, here the microcontroller can recognize a person is in the red on the top right corner, and no person on the top right corner to show in green. And also it can transfer to the real life setting to detect person versus no person, learned purely on the microcontroller. So those are some of the background, which I categorize them as Edge AI 1.0. Okay, so these models are highly specialized for different tasks. Like on the bottom, you have to train different models and different data for different tasks. And the lack of negative sample for training really makes on-device AI more challenging, with limited generalization and failure of corner cases. So with the advent of visual language model, Edge AI 2.0 enables this general knowledge with general models with world knowledge. Okay, general model means we train just one model to handle multiple modalities, multiple tasks. Those are enhanced by large language models world knowledge. Okay, I believe language is a very condensed version of knowledge, and learning from language can enhance those visual perception with advanced reasoning capabilities, instruction following proficiency, and they are even deployable on the edge. So I will talk about the whole pipeline by first training the multimodal. First talk about the multimodal pre-training method for VLA, the visual language model, and then followed by the quantization technique, the AWQ quantization approach for 4-bit quantization that can make a large VLA, a small VLA, so that we can deploy them on the edge device, adjacent or nano even with the TinyChat engine. So those are the 3 sections of the main talk. Let's start with VLA on pre-training for visual language models at this year's CVPR. So we find that the data and training recipe matters more than the architecture. So VLA is using the same architecture as LLaVA, but enabled many more interesting capabilities. For example, we find visual instruction tuning is not enough. We want to do visual language pre-training, okay, to unfreeze both the VIT, the projector, and also the LLM. Okay, and image text pairs are not enough, but interleaved image text data is very crucial. So here we have the image token, the language token with the projector, concatenate them together, but using the interleaved image text is very crucial. And the visual in-context learning requires unfreezing the LLM. So here we have 3 training steps: initializing the projector, interleave the pre-training, and visual text joint as FT. During the joint as FT phase, we find reblending the text-only data can recover those text-only capabilities. So those are some of the learnings from VLA. On the MMU benchmark, is on the text set is currently the best one on the open source category. So the yellow parts are closed source, and the blue green is ours. The white ones are the open source ones, and this is the overall score. There's a new benchmark called Video QA benchmark, Video MME. We also rank pretty top on the open source version, but it's behind Gemini and GPT-4o and GPT-4v, but not too far. So here are some examples of visual language model of the in-context learning and multi-image reasoning capability. Like giving the company logo, we can automatically deduct the task is to give the product name, and also the home to outstanding ramen. And here it can say home to the greatest pizza to talk about the food associated with the city. Versus multi-image understanding, which is a cool feature enabled by interleaved image text pair. For example, asking what is the total price of the beer, it can say the beer on the table is Magna by OCR, $6 each on the menu, and 2 of them by detection, and then it can tell it's $12 in total. So this is a visual chain of thought, like giving the prompt, think step by step, it can answer it correctly. And reasoning across multiple image as a new feature in VLA is critical. Like this case for environmental study, we can ask what is the implication of temperature. You can tell the temperature is getting warm because the Arctic ice is getting thinner from 84 to 12. VLA is also capable of video understanding thanks to the interleaved image text pair, interleaved image text data. For example, here, what might be the next step according to this video? It's going to say it's going to bake it in the oven. Similarly, in this case, what is likely to happen next, it can tell it's going to blend the strawberries in the blender, which can help building the world model for robotics to understand the world and next step. Likely here, what is likely happen next, and it's going to say it's grind and mix the ingredients together, which is actually having quite good reasoning capability and modeling the world. Like in this football game, I can tell what is happening in the video. The ball goes into the goal, celebrates with his teammates, the crowd cheers and hugs each other. Another example of VLA to help autonomous driving, where Sanya is going to present some of the demos as well. So we use this demo. Actually, I shot this video when I was driving the Tesla and just feed it to Vila to test our Vila's performance. I can say you should reduce the speed using the low beam headlights and keep the safe distance from other vehicles for handling such corner cases. Another example for Vila for autonomous driving, given this image, should you honk at the pedestrians crossing the road? It says it's not appropriate to honk, it's implied and disrespectful. We didn't learn those from the driving school, but we learned from textbooks when, so I think it's more efficient to combine these large language models with driving tasks, not only exterior, but also in the car, the driver monitor system. Is the driver distracted? Yes, the driver is distracted. This is the same model actually, but can handle a lot of different scenarios without having to train on particular data sets, showing pretty good generalization capabilities. There's an interesting case here for zero-shot learning Vila for healthcare. Will the practice cause pain to the patient in the image? And Vila says it's a simulation, not a real patient, does not cause pain. It's a mannequin, not a living person. And one of my friends went to Italy and sent me this image. And asked, where is this? It's going to say, you can correctly tell where it is, although it feels not quite straightforward, but showing the word knowledge is pretty good. And there's another example for Vila for video. According to the video, which finger does not need to press the strings when playing EM9. For those who know how to play guitar, watch the entire video and several tutorials. And finally, the middle finger is not used. How many kinds of chords are played with the video is going to say 7. So altogether it's shown 7 different chords. But the amazing stuff is we also enable Vila to be deployable on Jetson Orin, which is the edge computer by NVIDIA for driving applications. So we can deploy it locally on this edge device without using the cloud GPU for robotics applications, for driving applications. What is unusual about this scene is going to say there's several safety concerns. For example, wind turbine, and here in the factory, how many cars are jacked up? There are 2 cars jacked up in the image. There's a person whose head is under the car. What color is gloves? It's orange. So we can enable these edge AI applications using Vila on a wide range of tasks. So how do we deploy Vila, such a big model on Jetson Orin? So there are 2 considerations. The first one is to reduce the model size. The smallest of Vila is only 3 billion parameters. And the next one is 8 billion, 7 billion, 13 billion, all the way to 40 billion. And then we use a quantization technique, which I'm going to talk next, to further compress the model. So the 3 billion parameter Vila after quantization is only 1.5 gigabyte. So I'll first introduce smoothquant, a popular technique to quantize large language models. It's now available in NVIDIA TensorRT LLM. There's plenty of work on quantization in the CNH, but we find what is new for the large language model is that there are lots of activations that has huge outliers. They are having very big spikes in certain channels. Like here we have 3 channels that has big numbers that is going to clamp all the other, but it's going to waste the dynamic range because all the blue activations will be clamped to 0. But the weight is relatively quite easy to quantize. The range is, notice here is 5, but here is 70. So here we have a clever solution to actually migrate the quantization difficulty from activation to weight. Since matrix multiplication is linear, we can multiply the activation channel by a number like 0.1 and multiply the weight by a large number like 10. So my 0.1 times 10 is still 1 by 1. Thus, we can migrate the quantization difficulty from the activation to the weight. So the activation, you can see, is much smoother. The weight is a little bit bumpier, but still very easy to quantize. Here is a real world. Here is a simple example. We have the activation, 2 channels of outlier. We have 16 times the weight of 1. We find the square root of that to be the quantization scaling factor. so that we can quantize them so that 16 times 1 equal to 4 times 4. Okay, so they are still mathematically equal. Similar here, 8 times 1 equal to 2 times 4. Okay, so they're mathematically equal, but the tensor activation tensor here is much more smoother than the left. In practice, alpha 0.5 is a very good hyperparameter already, but if you want to do a little more carefully, you can actually search this scaling factor from 0 to 1, and then you multiply x with the s minus 1 and s on the right-hand side associated with w, so they cancel each other, okay? For having the inverse of w, s cancels each other, this can be folded into the weight, so no inference overhead. This can be folded into the epilogue of the previous activation layer, so no inference overhead if you implement them efficiently in the system, and the result is still mathematically equal. So that effectively get rid of the fine-tuning, and even without fine-tuning, we can very well recover the accuracy and having the same, even shorter latency, despite we can have 4 GPUs rather than 8 GPUs, and having the GPU memory. So without fine-tuning, reducing the number of GPUs by half and maintain the same latency. Okay, so that's the streaming, that's the smooth quant. What about on-device LLM? We find the key challenge is actually the weight memory. So the weight memory is bounding the inference latency. Okay, so especially at the low batch size, when we are deploying Vela on the edge, memory is bounded, and memory is bounded by the weight. So here, similar to the EIE, which I designed like 8 years ago, we use the 4-bit weight and 16-bit activation and 16-bit arithmetic so that we can focus on reducing the weight. And here we use the activation awareness to preserve the salient weight channel by scaling according to the activation magnitude, not the weight magnitude. As a result, we can deploy them on a laptop. And this is the key technique, key quantization technique behind NVIDIA's chat with RTX, where you can have a laptop and run large language model 7B, 13B locally on the laptop. So theoretically, from 16-bit to 4-bit, you can have 4x saving, and we have about 3x measured speed up compared with FP16. It also got a best paper award at MLSys, so I'm going to spend some time to talk about the details. Originally, using round to nearest, you have a big degradation of the perplexity. So how do we deal with that? Surprisingly, we find keeping only 1% of the channels unquantized can actually greatly improve the perplexity. But how do we select those salient channels? And can we also avoid those floating point numbers and mixed precision? Can we avoid that? Actually, conventional wisdom says if you're quantizing the activation, you should look at the activation, but actually quantizing the weight, you should look at the weight. But actually, we find it's helpful to look at the activations. Okay, if you just look at the weight, scaling according to the larger weight, you don't scale that. If the weight is large, then you don't quantize that. This recipe doesn't work well. Random recipe doesn't work well either. But there is a big improvement if you look at the activation. Okay, if the activation channel is large, then you don't quantize that weight channel. So that only solves the first issue. Look at the activation awareness. There's still the second issue. Okay, is it really necessary to introduce mixed precision? You need a specialized kernels. You need a different treatment for building a product. This is especially challenging for users to try introducing so many hyperparameters. Actually, we find mixed precision is not necessary. There is a more clever way to reduce the perplexity, which is by scaling up those salient channels. Okay, so the second channel is salient. We only need to scale it up, like by 1.5, by 2, by 4. The perplexity immediately drops. We're quite excited about that. And intuitively, this is due to if other channels remains the same, you're scaling up one channel by 2x, you are effectively adding one more bit. Imagine you have 0.5 and 1. Previously, they are both quantized to 1 if you use round to nearest. But if you multiply them by 2, 0.5 becomes 1, 1 becomes 2, and now you can distinguish 1 and 2. Okay, so you are effectively adding 1 more bit. So this is a mathematical equation why scaling up that channel, certain channels, not all of them, can reduce the quantization error. So we have a quantization scalar and determined by IDBS max. So the quantized version times the x equal to the scaling factor, thank you, times the rounding result and times the activation. So if we are scaling up the weight channel, okay, the rounding still error still stays the same because its minimum value is 0, max is 0.5, since 0.5 is the maximum rounding error. The mean is actually 0.25, okay, so it stays the same. But if you're scaling up the S, the total result will be smaller, assuming you are not scaling up everything, so the total dynamic range stays the same. So using this technique, we can effectively reduce the perplexity, and this can be also similarly implemented as smooth quant. So for building a product, it's super easy. If you have smooth quant, you can easily have AWQ using this mathematically equal equation to have S and S inverse multiplied with a W and X respectively. So it's performing quite well when we are doing the perplexity analysis. This is the number of calibration sequence with a smaller calibration sequence. The perplexity is much lower, and the generalization capability is quite well, since like GPTQ, which require calibration set and require backpropagation to do optimization, which tend to overfit. Ours doesn't overfit since it doesn't have any backpropagation. And using 2 different data sets, one for evaluation, one for calibration, the difference is much smaller, very close, even if you have different calibration and evaluation data sets, 0.5 versus like 4.8. This is the accuracy of AWQ for INT3, INT4, 5.6 versus the FP16, 5.47 perplexity, which is quite well maintained. So smooth quant and AWQ are now available in NVIDIA TensorRT LLM. TensorRT LLM is the state-of-the-art LLM inference framework from NVIDIA, and it can enable a Falcon 180B parameter model in a single H200 GPU using INT4 AWQ, thanks to the large model capacity, large memory, 141 gigabyte, and can fit 180 billion parameter model. And now it's quite widely used with over 1 million downloads from Hugging Face. We are actively maintaining that. We have also built a tutorial how to add support for new models. So feel free to check it out together with these companies. And finally, the last step, how do we deploy them? How do we implement the 4-bit quantized model? Since conventionally computer architectures, computers are byte aligned, the minimum units is 1 byte, is 8 bits. So handling the dequantization from 4-bit to 8-bit is very crucial. And how do we use the minimum number of instructions to dequantize the maximum number of weights? That's very crucial. So here, we use only 3 instructions, only 3 logical instructions to decode 32 numbers, okay, by this hardware-aware packing. So rather than arranging them in the linear manner, W31, 30 all the way to W0, we align them, or we pack them in an interleaved manner, okay? So W31 followed by W15 and W16, W0, okay? So we can mask it by 0f to look at the lowest number of bits, and then we can also shift the right by 4 bits and then mask it to decode the lower bit. Okay, so altogether we can use only 3 instructions, a shift, a mask, 2 masks to decode the 32 numbers, and it's much faster than if you don't use the interleaved packed weights. And also we implemented the fused kernel for attention and the fused kernel for jam to reduce the DRAM access. So compared with FP16, we are about 3x faster compared with FP16 on 4090 GPU, on laptop GPU, and also on Jetson Orin mobile GPU. We built a tiny chat computer actually, so that you can chat locally on a computer. We 3D printed this box. It's having a Jetson Orin Nano in the back, very cute. It runs the 7 billion parameter model with relatively real-time latency. So such data privacy and security is well maintained by such on-device. This is the on-device. This is the device. On-device deployment, even without internet for customization and personalization. So this is a demo running on the laptop. Feel free to download it. From TinyChat GitHub, it's available for both MacBook, Intel, and NVIDIA Book and different laptops. And to close the loop, TinyChat also supports visual language models. Okay, so we have this Llama 3 Vela 1.5 and Vela 1.5 13 billion parameter model. Okay, so FP16 in the 4, the A100 tokens per second is almost pretty much more than doubled. 4090 tripled, Orin also tripled, and the performance is actually very well maintained, accuracy very well maintained. And here you can interact with the image, like what is unusual in this image. There are lots of deers. Have to be careful crossing the roads, and should the driver keep going, and it's going to say no, the driver should not keep going because of the deers. Okay, and also we can run visual language model on your MacBook. All right, to summarize, we talk about Edge AI 2.0 with the visual language model. Okay, we need a full stack optimization with 3 parts, from training and application side, and also on the system and hardware and inference side. On training, we talk about this training recipe called Vela, a visual language model, Vela. It's actually driving up the demand for computing. Model compression bridge the gap between the supply and demand of computing. By using 4-bit AWQ, we turn a large model into a smaller one so that it can alleviate the memory bandwidth limitation. And followed by the TinyChat efficient inference library, we can quickly deploy them and using a byte-aligned computer to perform such system and co-design to enable the theoretical saving from 4-bit quantization into measured speedup. All right, that's all my presentation. Thank you.
Thank you. Very impressive work, and glad to see that so much of it is open sourced as well. Any audience questions? If audience asks a question, could you please repeat it as well? Yes.
So the question, let me repeat. The question is, do I specifically quantize LLM part or the VIT part? I didn't quantize the vision part because we profiled the latency, and it occupies more than 95% of the latency. So we only quantize the LLM part. For visual part, I believe it is relatively mature technique to quantize those visual models. Yes, we have tried the diffusion model to quantize diffusion model also using the smooth quant. So that technique, that intuition to migrate the quantization difficulty is irrespective of vision task or language task. As long as transformer matrix multiplication, the same principle will hold.
So are you also working on reducing the size of the weights? I mean, the amount of the weights. Are you also working on it?
Right. So at NVIDIA, we're also working on that part. So there are 2 challenges. One, actually, one challenge is the fine tuning. We find for quantization, it's a low-hanging fruit because you don't need fine tune. And for reducing the weight, you need a fine tuning to reduce the accuracy drop. And either using pruning or architecture search, actually NVIDIA has this technique using this once-for-all approach to generate many sub-networks that can independently operate, generalize it from CNNs to large language models as well. But that requires fine tuning.
Right, one last question.
Thank you so much for the talk. I was wondering what is the most standard way of measuring the efficiency of ML models? Is it like floating point operations, or should we directly measure the latency on device? So what's the most standard way to calculate efficiency?
Yeah, there is a good benchmark called MLPerf, which is the industry, like Olympia game from the industry. So there are several dimensions. Okay, one is the throughput, one is the latency. Okay, a single batch and large batch, you have to consider both of them. For single batch is memory bounded. For large batch is sometimes even compute bounded. So you have to consider both. And also there's the open track and the closed track. Closed track, you cannot change the model architecture, you can do quantization. But open track, you can also do pruning, you can also do neural architecture search. So feel free to check out the MLPerf benchmark with some standard workloads.
Can you hear me now?
Yeah, I think you're good.
Cool.
Sean is unmuted.
Yes. Beautiful. Okay.
Please go ahead.
Yeah. Yeah, as I said, we tried our best to contribute to this space in the past. And yeah, yesterday I actually realized that there's a lot of diffusion talk, distillation talks in this workshop. So I last minute added some other stuff to make it a little bit less focused on distillation. I think we had like Sergey's talk before, and I think Tim's on different distillation methods. I'll add our perspective to that, which is based on adversarial training, which really enables like super fast synthesis in 1 or 2 steps, but also talk a bit about other stuff. So I think it's pretty impressive actually where we got so far. So this is a sample from a text-to-image model, and today these models are able to generate very complex scenes. You can really dive in, you can explore what's going on. There's so much interactions happening, and the same is obviously also true for stuff like this. This is pretty famous sample from Sora. We have like cars driving in the background, this couple here walking hand in hand, people walking, talking on the streets. And today, Runway announced their Gen 3 model with this super impressive sample, which is a middle-aged, sad, bald man becomes happy as a wig of curly hair and sunglasses falls suddenly on his head. And this is, I think, it is super impressive. It really follows this prompt quite well. And what all of these have in common is that we got there through one major ingredient, which is scaling, obviously. So the architectures and the algorithms that we use to train these image and video generation models, they're pretty scalable. We have a lot of data available in both domains. We have the scalable algorithm, which is diffusion. It has a stable pre-training objective. And we have scalable architectures. And this combination is very much the ingredient that, these are the ingredients that you need to achieve like this high quality. On the left here is this standard or classic plot from the GPT-3 paper, which really visualizes the scaling laws. And on the right, we have something from the diffusion transformer paper, which also shows that model quality, sample quality increases when you increase either the model size or the sequence length. So both contribute to the amount of flops that go into the model during training, or you can, of course, also just increase both. And yeah, this works pretty well. So question could be, is that all we need? Are we done? And I think to some, yeah, that is an answer. If you're just interested in raw performance and have like a lot of money, a lot of compute, then that is a very reasonable way. But obviously, there's not all institutions have infinite money or infinite compute. If you train a large model, that is typically on the order of millions of dollars to train. So one major motivation is to find still very scalable training algorithms, but make them more efficient. So you want to make sure that you're not wasting your precious compute and stuff that your model can't really capture, or that you as the end user of the model don't really care about. The other is inference. So with these state-of-the-art models, image generation is typically on the order of seconds. Video generation is on the order of minutes. We don't really know for Sora and Gen 3. For Luma, which is another video model that was released last week, it's 2 minutes. So yeah, it's pretty slow. It's far away from the real-time experience that Sergey just talked about. And I think that motivates another field of research, which is just like finding these more efficient sampling methods for these pre-trained models. So this is what I want to talk about. First part is some work that we did on finding more efficient and scalable training algorithms, models. And the second part will be about these more efficient sampling methods. And the first one is from this paper here that we published in March, scaling rectified flow transformers for high-resolution image synthesis. And basically our motivation for this was that back in November, we were really sure that we wanted to scale up our models to larger sizes. Before that, we had published SCXL, which was, it's a medium, I think in today's standard, probably a small model. And yeah, we really wanted to scale it up. But on the other hand, we didn't have infinite resources. So before we went into the full scaling phase, we were really asking ourselves, what kind of diffusion formalism do we actually want to scale? What kind of architecture do we want to use? And there's, especially in the diffusion field, there's so many different formulations, right? You have the classic DDPM, you have an epsilon prediction, you have V prediction, you have EDM, you have stochastic differential equations. There's so many different formulations of sometimes of the same thing. Sometimes they're a bit different. So there's really this zoo of different formalisms. On the other hand, you have different architectures. Stable diffusion, for example, was based on a UNet, convolutional UNet. More recently, shifting towards transformer-based models. So yeah, the diffusion transformer that I mentioned before, it's one example. It's just like pure transformer. Other examples are something called UVIT, which is a mix of a few convolutional layers and a transformer model. So also there's like this zoo of different architectures, and we really wanted to make sure to find out what is actually for our use case, text image synthesis, the best approach, such that we don't waste training compute. And yeah, before I go into that, I want to do like a quick intro actually, or recap, or to flow matching, because that's what we ended up using in the end. So I'm pretty sure that most of you have seen this this formula. This is just a way to construct your training data for a diffusion model typically. So you have some training data, the training data distribution P data, you sample the data point from that, and then you add noise to it. And you do that by a so-called noise schedule, which is defined through these prefactors AT and BT. And yeah, depending on how you choose like AT and BT, you can recover these classic formulations like EDM, DDPM, reprediction, and stuff like this. But one of the methods that we also ended up using in the end, that's gaining like more popularity recently, is this so-called rectified flow. It belongs to the class of flow matching models. And that one basically just interpolates between your data and noise. So AT is 1 minus T, BT is T, T runs from 0 to 1. If you plug that into the loss formulation for your conditional flow matching, you actually end up with this loss, which just means that your prediction target for your neural network is the vector that points from data to noise. And after you've trained with that, you can sample from the model by just solving this differential equation. And on this slide, you basically have all the ingredients for implementing this rectified flow framework. It's super simple. That's why I'm a huge fan of it. It removes a lot of the unnecessary theoretical overhead that you have in diffusion formalisms or formulations. And it's actually also more general than diffusion models. Just like very quick as an overview, it is It's not necessarily restricted to that forward path that I had on this slide here. You can basically interpolate between different distributions as you wish. The one that I have chosen here is the one where you can recover classical Gaussian diffusion. But yeah, you can basically use everything. And that makes for interesting applications, like you could interpolate between a low resolution and a high resolution image if you want to do something like upscaling or different stuff like this. I think this just has a lot of flexibility. But the main feature of it is, in my opinion, that it's much simpler. So yeah, we do not need these complicated frameworks anymore. And we can just write this down in a few lines of code. Super straightforward to implement. So yeah, I'm a huge fan of that. Can highly recommend to look into these papers. They basically all discovered the same thing at the same time. And yeah, that's what we also ended up investigating in addition to the classic formalisms. And one thing that made the initial diffusion model super successful in the beginning was DDPM in 2020, was that it implicitly discarded scales, noise scales, that were perceptually irrelevant. So the loss was designed in a way such that it was trained on the relevant, perceptually relevant scales per default, which just makes the training cycle more efficient. And we were asking ourselves, the same might be true for this rectified flow formalism here, especially if you consider that for the endpoints of the trajectory, so for t = 0 and t = 1, you're either predicting the best solution to predict is either the noise mean or the data mean, and there's then not much more to be learned. So one intuition that you can derive from this is that you don't want to sample all of these levels uniformly, because then you're wasting compute and stuff that you don't really count for or reduce, or which is basically trivial to predict. But you rather want to focus on the scales in the middle of the schedule. And this is what we did here. We chose a distribution to parameterize the sampling, the time step sampling distribution with this log normal distribution. This has two parameters, mean and the variance. And those you can tune to kind of bias the time steps either towards higher noise scales or towards lower noise scales. It gives you some flexibility to investigate which noise scales really matter during training. And then we trained a few models and compared that to classic epsilon prediction with a linear schedule, reprediction with a cosine schedule, EDM, all these diffusion formalisms. And actually in this setting, I think this was class conditional synthesis and ImageNet latent diffusion. We found that the rectified flow with this new focused sampler gave the best results. You also see that the rectified flow formalism, this is just a feature by which it has per default, is better in the low step regime. So between 10 and 20 steps, it achieves the best results. And yeah, especially around 10 steps, it is still quite good. All right, so that is on finding more efficient noise scales to sample from during training. The other thing is that I mentioned in the beginning is we had like these different architectures, right? So UNet, UBIT, DIT, different, especially with UNets, there's like so many different hyperparameters that you can tune if you want to scale up. That kind of makes it impossible to search the full space. So we actually ended up discarding the UNet and just looked at different transformer-based implementations, which is the UBIT, DIT, a variant which has cross-attention layers from the text embeddings. And then something that we developed for this paper, which we called MMDIT, multimodal diffusion transformer. And this model, since we were doing text image synthesis, treats the two different modalities, text embeddings and image embeddings, in two separate streams within the transformer model. So we have weights that handle text embeddings, weights that handle the image embeddings, and then in each block they are joined through a joint attention layer. So that model has the same, basically the same amount of flops as a classic DIT, but doubles the amount of parameters. And if you look at the metrics here that we calculated over the course of training, you see that this architecture actually performs best. So that's what we used, and then scaled up. And we got some pretty nice scaling plots, I would say. As an aside, we also found that the validation loss is actually a strong predictor of model performance. So you don't really need to sample the model, which is usually kind of slow and a bit tedious to do during the training. But this is actually nice because the validation loss is something that you can compute in a forward pass. So yeah, and if you plot that validation loss for different model sizes, we get a clear scaling trend, which is pretty nice to see. And of course, this is much more interesting. Samples from the model. This was the largest model we trained then, was an 8B model, which was pretty competitive with state-of-the-art text image models like Midjourney and Ideogram. And it also solved this problem that a lot of models have solved in the meantime, which is the text rendering, where one aspect, as we think, is that it really has like this dedicated text transformer stream. All right, but this brings me to the second part. So we have this nice model. It's actually quite huge. If you want to sample from it, it's pretty slow. Usually, even on like very modern hardware, like A100s, H100s, you have to wait a few seconds to get a sample out. You still have to use multiple steps, like 50 steps, to get the best results. And this is, yeah, it can be pretty frustrating, especially when you're designing a talk. And then I realized, oh man, this has a classic AI hand here if you look at it. So I did it again. The laptop is still floating in the air. But yeah, I think you get the point. So we want faster synthesis. And we've seen a bunch of things now here in the workshop. But the one that I want to talk about is this adversarial diffusion distillation, which is a line of work that we contributed to this distillation research. And it actually started with a failure. So we really wanted to get to like one-step text-to-image synthesis. And our first approach to this was something that one of my co-workers, Axel, has a lot of experience in, which is pure GAN training. So he had done like this work StyleGAN-T at NVIDIA, which is a large-scale text-to-image pure GAN model. And we said, okay, let's try this. Let's make it even better. But yeah, as you can see here after training, and we actually spent a lot of time and resources on it, it didn't really look super good. It is okay, but it has quality issues and it has mode collapse issues. The face of this teddy bear here looks always the same. Same for this prompt, which is one of our favorite testing prompts. Cinematic shot of Professor Sloth wearing a tuxedo at a barbecue party. Yeah, it's not really something that you, I don't know, want to publish as some high quality results. So we looked into other stuff that was out there. One is consistency models and consistency distillation. There was this model LCM-XL, which is a latent consistency model applied to Stable Diffusion XL. And actually for this model, the one-step samples looked already pretty decent. Yeah, so you could see like diversity and structure, except for the fact that obviously the quality isn't there. It's blurry. And yeah, kind of one intuition that you can have when you look at the stuff is that from very far away it kind of looks as you just would need to add a bit of image detail to it and then you're done. So that was our motivation, which we thought, okay, where we thought, yeah, let's use this and combine it with an adversarial objective. And this ended up being our method here, adversarial diffusion distillation ADD, where we started from Stable Diffusion XL as a teacher model, initialized a student model, and I'm just talking about the unit here, from the same weights, and then combined two different losses, a distillation loss, which just is, which just tells the student to match the teacher output for certain time steps, and an adversarial loss, which we implemented through a discriminator. That discriminator was based on the same discriminator as the Steigen T discriminator, which is based on features of DynoV2, a convolutional network. So for that, we had to go into pixel space, apply it, and then calculate the loss. And yeah, that really improved the results over this LCM method. So these are, again, one-step samples, and we see that they're much crisper. That was pretty good, actually. I like when my coworker first shared a notebook with us where he demonstrated the inference. I actually couldn't really believe it, how good it was, because I thought there must be a mistake, but it was just a single step. So it was really nice. The other nice feature about this is that we can maybe actually see how it works here, is that it reduces the output diversity of the teacher quite a bit, but it's able to achieve a bit higher image quality and crispness. So in the bottom, we see a sample from the teacher, or 4 samples from the teacher. In the top, we see 4 from the trained student. And yeah, the images are crisper, but the diversity, the poses are much less, it's much less diverse. Same for this. The problem with this is that this approach is not really scalable, because as I said, we had to decode into pixel space to apply this DynoVT based discriminator backbone. And that discriminator backbone was also is only applicable on a fixed resolution. So you can't really, which is I think 518 pixels. So you can't really go beyond that. Nowadays, the standard in text image is at least 1 megapixel generation. So yeah, that makes it pretty hard to scale. And especially the fact that we go out into pixel space, backpropagate through all of these steps, makes the training really, really expensive, and you can't really go to larger models. Well, it's just very a lot of work. So this motivated our follow-up work to this first adversarial distillation work, which is a latent adversarial diffusion distillation, and kind of natural evolution, I would say. Like the main motivation was we should really avoid the decoding step into the pixel space. And you usually get the best results in these adversarial training scenarios when you have like some pre-trained feature extractor where you can start from, right? That was in the previous method. ADD was just a DynoV2 discriminator. In the latent space, you usually don't have that. So we thought, okay, let's use the pre-trained diffusion model, which is our teacher anyways, as a feature extractor. And that's what we tried here. So we have the teacher on the one side, and the discriminator, but it's actually the same model, except for the fact that the discriminator has some learnable heads on each of the layers where we extract features from. And then we compute the adversarial loss based on these learned features. We also initialize the student from the teacher model again. Like this is all the same transformer architecture. So yeah, we also switched to the transformer-based architecture that we did for Stable Diffusion 3. This was not the unit from SDXL anymore. And another nice feature about this is that it is like modality agnostic, because since it's a transformer, it just operates on sequences. So you can also use this for video, for example. And it also natively supports multi-aspect resolution, high resolution, because we don't have to decode into pixel space. And that means we can distill much larger models. And yeah, it also enabled us to get rid of the distillation loss, which is kind of a debatable thing to do, because adversarial training some people think it's a bit of a hack. Some not. I think it's actually great for achieving this under constrained resources. Yeah, what we saw is that actually the setting with just the adversarial loss without the distillation loss works best. And since we were using this pre-trained diffusion model as our feature extractor for the discriminator, another property that this model has is that we can actually, during training, control which scale the discriminator should focus on. Because since yeah, since it's using these diffusion features, you already have to pass in a time step and yeah, a noise latent. And if you pass in very high time steps or noisy latents, then usually these correspond to low frequency features. And if it's low noise scale, it typically corresponds to high frequency features. So we can bias the discriminator into certain directions. We did that again with this log normal distribution that I described earlier. And yeah, we found that we actually have to shift the schedule a bit to the right to higher noise scales to achieve the best results with this technique. And then a last ingredient that also helped here is to apply direct reference optimization. So both to the teacher model and the student initialization, but also after training the adversarial student, we can reapply the LoRa weights that we trained to achieve the DPO version of the model to the trained student, and that actually works out of the box. It's a bit of a merge magic hack, but yeah, in this case here, it further improved the quality. And yeah, if we run some user studies on this outperforms other methods like LCMXL, STXL Lightning, our own model STXL Turbo, both in prompt alignment and just image quality. And yeah, some samples from this model. So we see it is actually these are not one step. To be fair, these are two step and 4-step samples. But it retains the ability to spell. It's pretty diverse still. There's a lot of styles in it. It's it's really nice. But it comes with a few limitations. One is that the prompt following is not as good anymore. So sometimes it fails for like these more difficult prompts. So obviously one thing to fix is exactly that, just improve the distillation methods, find better algorithms, maybe combine it with stuff like new distillation techniques like moment matching. Yeah, then there's always the debate of getting rid of the adversarial training. I think right now, and in the regime of small models or models with like limited capacity, we probably always need it, because these regression-based objectives that we have in other distillation techniques, they kind of, if your model doesn't have enough capacity, you will always end up with something blurry. And the adversarial training is one way to circumvent that. Then you get like other trade-offs, but it's like one way to get like at least crisp image quality out of such a distilled model. And then obviously the other thing is applying that to video generation. I think having something like real-time text-to-image video generation is an extremely attractive thought. So I think I'm out of time. I actually wanted to talk a little bit about video generation, but I'll skip that. Actually, I have another talk at the AI for content creation workshop later today. So if you want to go there, then you can. And yeah, maybe one thing, which is this general question of which was raised the announcement of, or maybe even before, but at least this announcement here of GPT-4o, which can do multimodal generation. It's a question of what's actually the status of diffusion versus autoregressive training. And autoregression actually has although like all of this that I was talking about is based on diffusion, right, of flow matching. Autoregression has a few advantages. It is like, one thing is there's massive research going on in optimizing the inference, optimizing the training. There's even dedicated hardware being built for this kind of stuff. Seems to be like an advantage for it. The training efficiency is much larger because you train on all the token transition probabilities at the same time in autoregression, whereas in a diffusion model, you only sample a single time step and then denoise that. So the training signal in diffusion models is much sparser. And that means you just need to train for much longer to achieve the same quality. And then they also have different inference behavior, right? In autoregressive models, you can cache the intermediate activations and only have to recompute them for the new token. In diffusion models, you usually have to put the whole sequence through the model again and again for each denoising step. But then on the other hand, to really have like high quality autoregressive generation, you would need some really good tokenization. And that's where the current bottleneck is for these methods. And they also don't have like this native support for image editing, image appending that diffusion models have. It's a bit of an open question, but I think it's very interesting to consider. We might see a comeback of autoregressive models. I don't know. Maybe a combination of the two. And yeah, that's basically it. If you have any questions, feel free to ask them.
I think we have time for say a few questions.
Thanks, Scott. I have a couple of questions about the principle that you presented, still free.
Yep.
The first one is compared to prior methods, you have this additional text branch to keep updating. So I was wondering how expensive that is at inference or in terms of computation compared to using its text embedding. So or then it's really worth it. That's the first question. The other question is about the data that you use. I was wondering whether you are using any synthetic data generated by like larger models, and if so, do you have a recipe to like replicate that sort of paper to data?
Yeah, good questions. So on the first,
Can you repeat?
oh yeah, sorry, yeah. First question was on the multimodal DIT architecture with the two transformer streams and on their efficiency. It's a really good question. So the efficiency is, let's say you compare, for example, training iteration speed. It is actually quite similar as in the base model. But I would say if you scale to really large architectures, you might want to reconsider this choice. Because these dual streams provide kind of an inductive bias, and at very large scales, you don't really care about it, or you don't really want inductive biases in your model. So maybe something to reconsider, maybe do a combination of this plus very classic diffusion transformer. Yeah. The second question, synthetic data. Yeah, I didn't mention it, but for the second approach that we had, this latent adversarial diffusion distillation, that was actually trained exclusively on synthetic data that was generated before training on from the ST3 teacher model. So that is something that works really well. Like an advantage of that is that you stay strictly in distribution of your teacher, which makes the training task a bit simpler. On the other hand, it kind of prevents improving upon the teacher because you can't incorporate real data. But there's a bit of this trade-off. But yeah, it's definitely possible to include these kind of data.
Yeah, I have a follow-up question. I was wondering whether you have a recipe to generate such data, like how you select text prompts for it.
Okay, question is, what's the recipe to generate the synthetic data? One answer is to simply use, you have some data set that you train your base model on. You can just use these prompts. You can also use, if you have data sets of prompts that are really popular, then maybe it's something that you want and you kind of implicitly get a preference optimization into it. Yeah, different methods. But I would, like, the simplest is to just go with your training data prompts.
All right. Let's thank our speaker again. Up next, we are moving on to Spotlight Talks. Don't leave yet. Lunch is until 1:45, so we have plenty of time. Thanks.